All right, so yesterday we finished up talking about amino acid synthesis. And the first few reactions we said were pretty old school. There was a Helb-Volhard-Zielinski one where you run up to this problem of a racemic mixture and then you have to purify it. Same thing with the malonic ester variant. You can use this, but again, you're getting a racemic mixture that you have to purify. So both of those aren't super common. There's also the Strecker synthesis. That's another relatively obscure one where, again, you have to purify it. The most common ones you see nowadays are these enantioselective synthesis reactions where you use chiral catalysts. The reason for this is you get much, much higher yields of your desired enantiomer. These chiral catalysts are somewhat expensive, but you can recover the ruthenium, and oftentimes they can be reused over and over again. So this is the preferred way for amino acid synthesis, but today we're going to talk about peptide synthesis, so linking amino acids together. So peptide synthesis is really complicated. We're going to go over the bare bones basics, and then I'll kind of tease you guys with the more advanced chemistry that we're not going to cover. So let's go over the bare bones basics, and I'll show you guys the problems with this. So the first problem is, let's say we want to couple together this amino acid plus this amine and form a peptide bond. Will that work? So can I just mix these two together and get an amide out?
No.
No, why not?
Because your voice tone told me no.
Because my voice tone? Because I labeled it as problem 1. What will happen?
I don't know. Once you have unfavorable conditions, you need acid.
What were you saying, Althea?
Acid-base chemistry?
Yeah, exactly. Amines are basic, carboxylic acids are acidic. So really all that will happen is a proton transfer. So what would a good solution be in order to avoid this proton transfer? What could we maybe do to our carboxylic acid? Do what?
Deprotonate it.
Well, if we deprotonate it, we still can't do nucleophilic acyl substitution. This really isn't a good leaving group.
Convert it to an acyl form.
Yeah, exactly. So we must turn our OH on our carboxylic acid into a good leaving group. And there's a couple different ways you can do this. You can use thionyl chloride, which we saw, so SOCl2, or you can use a peptide coupling reagent. There are dozens and dozens and dozens of peptide coupling reagents out there. I'm just going to show you one of them to give you an idea of how they work. So let's take a look at peptide coupling reagents. So the first one I'm going to show you involves a peptide coupling reagent called DCC, or dicyclohexocarbodiimide. It's a mouthful. And I'll show you guys what it looks like. So the first thing you do is you have your carboxylic acid, and then you have this other reagent. It looks like this. This is your dicyclohexyl carbodiimide. People just call this DCC. And in the first step of this reaction, all you're going to do is a proton transfer. So these nitrogens on your DCC can reach out, grab the proton off of your carboxylic acid, and give you your carboxylate salt. And I'm going to show you guys a shorthand trick. I'm just going to call these CY for cyclohexyl. So now we've got this carboxylate salt. Oop. And we've got this protonated DCC over here. where this nitrogen now has a positive charge. Okay, so now in this next step, this oxygen can attack this carbon and kick up electrons over to that nitrogen. And we're starting to convert that oxygen into a better leaving group, but we have to do a couple of transfers first. So the next step involves addition of your amine. So I'll call this RNH2 and I'll label it as blue so we can keep track of everything. So we're going to kick this up and attack that carbonyl. Oh. Shoot, I forgot a carbon. Excuse me. And then down here we would have our nitrogen with our two hydrogens coming off of it and our R group. And the next step is going to involve a proton transfer. So I'll go plus or minus H plus. And we're going to shuttle that proton over to the other nitrogen on our DCC reagent. So I'll show you guys by highlighting which proton's moving where. So the nitrogen that was on the amine is now coming off of this position. And our amine is now neutral that was added in. And we've got this R group coming off of it. All right, now we're ready to do the shove off. Okay, so in this step, this oxygen will clamp down. This will pop over, and we'll kick that over. Now we've got our new amide, and the byproduct that we get out of this is unique. So it's got an oxygen here. Oop. This is a urea leaving group. You may be wondering, why the heck did they come up with this reagent? It looks like a lot of work, a lot of steps. Not quite. The reality is these are actually really easy to clean up. So oftentimes all you have to do is a set funnel extraction and you can get your purified amide out and all of your byproducts will go into the other layer. So depending on the peptide coupling reagents you use, you can do this really, really cleanly in one step. It's a very easy reaction. You may be saying, why not use thionyl chloride? Thionyl chloride is actually really challenging to work with, and you usually have to purify it even before you can use it in a reaction. So this is a bench-stable reagent, really easy to clean up. It's something that you see in a lot of organic chemistry labs and a lot of biochemistry labs. Does that make sense? I know it's pretty steppy. Okay, that's the only peptide coupling reagent I'm going to show you guys, though. I figured I should show you one. So let's jump into another problem.
Do they all work very similar to this then?
They all work fairly similar. There are some that are way different. So there's, oh my gosh. I remember I went through like 3 weeks in grad school trying a new one every day to see what would give me the highest yields. There's so many out there. And there's tons of them out there. Depending on the type of peptide bond you want to use, there's like one specific for it. So people have really optimized these. So let's go into problem 2. We already solved converting the OH into a better leaving group. But problem 2 is also a pretty serious problem. So let's say I have this amino acid. I'm not even going to bother showing stereochemistry at this point. I'm just going to call this an R group. And I want to react it with this amino acid. And let's say I've decided I'm going to use DCC, my peptide coupling reagent, and I want to link it so that there's a black amino acid for the N terminus, meaning I want the nitrogen to end right here. And I want to link these two together. Will that work very readily? No? Why not?
It could attack itself.
It could attack itself? Yeah, exactly. So with DCC, you'd run into a problem. So for example, this isn't the most colorful. You could run into one where it just couples with itself. Right? So that's one option. Actually, I'm going to clean this up. I don't like the way it looks. That's one option. Another option is that it will react with the blue one the way you want. Oh, sorry, this should be blue. Darn it. And you get the peptide bond that you were interested in. However, you'd end up with one that was also two blues. And then you'd end up with one that would be blue plus black, right? So really, you'd try to mix this together, you get 4 different products out of it. That's a big problem, right? We don't want to take a 75% hit every time we want to couple amino acids together. So what do you guys think a solution might be?
Do a protecting group off that nitrogen?
Yeah, protecting groups, right? So if we want these to quote unquote be our sticky ends and link them together, that means we must block these other groups. All right, so there are special protecting groups for the N terminus of amino acids and the C terminus of amino acids that are very different. There's a whole bunch of different ones. Again, I'm just going to focus on the 2 most common ones that you're most likely to see. So let's take a look at protecting groups for amines first. You guys have actually seen this protecting group on a few pods before, but does anybody remember seeing BOC written down?
Nope.
So BOC is a protecting group that's really common for amines. And what this stands for is tert butyloxy carbonyl. So a BOC group, when you look at it, typically looks like this coming off of it. So this whole thing right here would be considered a BOC protecting group. And it's really, really good for protecting amines. So I'll show you guys how to do that. And we're not going to go through the full mechanism. But in order to install this, you're going to use something called BOC anhydride. So let's write down the name of that. You may also see this written as BOC 2O. So it can be written a few different ways. There's other reagents that can also be used for installing Bach groups, but these are pretty common. And really all you're going to do is protect the amine. The carboxylic acid is going to remain untouched. I want you to know what the protecting group is and what the reagent is for installing the protecting group. So right now we've got this Bach protecting group off of that nitrogen, meaning it won't do acid-base chemistry anymore. The really cool thing with this is you can remove it using trifluoroacetic acid. So if you want to just go back to your starting material, you need this strong acid that's available in most labs. People will call it TFA or trifluoroacetic acid. And that will pop off that Bach group. The neat thing with this is you blow off a gas called isobutylene. So it's a pretty unique mechanism. If you get a chance to go through your textbook, it's worth taking a look at, but it's pretty novel. So you can protect your nitrogen and then deprotect it once you're ready to react that one side group. This is known as a carbamate. It's kind of half ester, half amide. So they call it a carbamate. You've got a nitrogen off of one end and an oxygen off of another end. So it is a new functional group that we haven't really seen before. All right, now let's take a look at protecting groups for carboxylic acids. They're a little bit different than for alcohols. What was the protecting group we used for alcohols?
OTSL.
So tosyl chloride converted an alcohol to a good leaving group.
Is that
Was it-
trimethylsilyl?
Trimethylsilyl. So TMS was a protecting group for alcohols. You really don't see it used for carboxylic acid, so we have to use a different one. So let's take a look at that one. All right, so the protecting group for carboxylic acids is really straightforward. I'm going to draw our amino acid out. All you do is treat this with catalytic acid and benzyl alcohol. What do you think will happen to that carboxylic acid moiety? What will it turn into? Looks a lot like a Fischer esterification, right? We've got an alcohol and a carboxylic acid. You guys did this in lab. Okay, so now we've got that on there. The neat thing with this one is, again, we need to be able to selectively remove this under relatively stable conditions. We can't use anything too exotic. So one way of doing this is to use H2 and platinum.
You said it's not.
That's actually pretty gentle for removing a protecting group. You can use HBr.
Platinum's expensive.
It's catalytic. And acetic acid. That works well. Or you can use sodium hydroxide and water. So it really depends on the amino acids you're dealing with. You don't want to accidentally cause side reactions, so you want to choose the appropriate reagent. So this is called a benzyl protecting group. All right, third problem is pretty obvious at this point. So imagine you're a chemist and your boss says, I want you to make this peptide sequence that's 15 peptides long, and you're like, wait, what? You want me to protect and deprotect this over and over and over and over again? This sort of chemistry takes a long time to do. So time is a huge issue. It's not easy. Number 2 is cost. If you have to spend that amount of time, you have to pay chemists, you have to buy all these reagents, you have to purify it after every step. It takes a long time. The third one is greenness. If you think about atom economy, deprotecting, protecting, deprotecting, protecting, deprotecting, protecting isn't exactly green, right? Biology does it way better than human beings. So I wanted to give you guys this perspective here. So Fusion is an HIV drug. It's a polypeptide HIV drug. In order to make Fusion using peptide coupling and protection, deprotection schemes, it would take 114 reactions. Which in and of itself sounds pretty daunting, right? I wouldn't want to have to do 114 reactions. The other weird thing to think about is if every step got a 95% yield, which I would say is pretty dang good, the overall yield would be 0.3%. Pretty abysmal, right? So Fusion is one of these classic examples of drug companies trying to figure out more economical ways of producing these drugs. Fusion is the frontline drug for HIV, meaning if your HIV is resistant to all other treatments, it's the last resort drug. To take this drug costs over $30,000 a year, and you have to get injected oftentimes once a day if you've got a severe case. The crazy thing is this drug is so effective that it will drop your viral load to undetectable levels. So it's a miracle drug, but it is super duper expensive to produce and manufacture. So chemists have been working on this for a long time, trying to figure out how to scale up these reactions. So now let's talk about solutions. Does anybody know one of the solutions?
Bacteria.
E. coli or bacteria, right? So directed evolution. Of yeast or E. coli. Those are the two most common ones. So basically you can try to force them to evolve into a way where they exclusively start kicking out one type of polypeptide. That's pretty dang challenging, right? It's not easy. You have to go through a lot of samples. Does anybody know a newer one that's been out a lot recently? Yeah, so plasmids. So plasmid transfer of genes. So basically you can try to push in a gene that you want expressed as a protein, right? Does anybody know the newer one? Sounds like a cookie. CRISPR? Have you guys heard about CRISPR?
Yeah.
This is like the ultimate game changer out there. CRISPR, you can basically get a kit on the internet for $100, $200 and basically tell bacteria to grow something for you. It's a huge thing in the chemistry and biology community right now. If you get a chance to read about it, it's both really exciting and really terrifying. We're kind of opening up Pandora's box with what we're able to do nowadays. So CRISPR, Cas9. I shouldn't leave out Cas9. That would be mean. So that's one of them. And then the other one, too, that's getting pretty common now is automation. So now we just have these machines where you can actually go in and you can type a polypeptide sequence and it'll say, okay, and it will just go and make it for you. The reality is very few chemists are willing to sit at a bench top and do 114 reactions to make a polypeptide, right? So automation is a big one. So these are kind of the solutions that everybody's looking at right now. Arguably, CRISPR-Cas9 is the one that most people are excited about right now, and chances are in the next few years we'll hear more and more about it. But I did want to show you guys the solid phase peptide synthesis, and you don't have to write it down. I just think it's a really interesting example. So this is called the Merrifield solid phase peptide synthesis. They developed this in, I think it was like 1969, and he won the Nobel Prize in the 1980s for making some unique proteins. But what he did was he took polystyrene and functionalized it, right? So plastic beads in a column. And you can see down here, each of them has a chlorine coming off of it. So you can do SN2 chemistry really readily. And then what he would do is he would get a big bottle of this amino acid reagent that was already Bach protected. So it's pretty easy to Bach protect one amino acid in bulk. And then what would you think would happen in the next step?
It turns into
Looking at the products?
Like SN2.
Yeah, it looks like just basic SN2. So you could kick that off. Now you've got your amino acid appended to your polystyrene beads, which is great. After this step, you would flush it with a bunch of water, make sure all of the excess residue was flushed away. And then he had these nice pure amino acids on the benzene. All right, and then the next step, he wanted to get rid of the Bach group. How could he get rid of this Bach group? TFA. So with TFA, you could remove this Bach group right here off of all of the amino acid residues. Oh no. Oh no, it erased. So I'm just going to call this R and then NH2. And then what he could do now is just throw in more of your next amino acid that was already Bach protected. Do a peptide coupling reaction using what reagent? DCC. So he'd mix these two together, then he could do a peptide coupling reaction. Now he had a dipeptide that was appended onto polystyrene. And then TFA to get your amine. And then repeat. Right? So he could grow these really long polypeptides off of polystyrene beads. And then as soon as he was happy with the peptide that he had, he could kick it off using hydrofluoric acid and get a free polypeptide. So HF isn't something you want to mess around with, but in this case it worked really well. He was reporting yields in the high teens, which nobody had ever heard of at that time for peptides that long. Normally people were getting down into like below 0.5%. So somebody reporting yields of these big, long, complicated polypeptides in the teens was pretty remarkable. And that started this big exploration of synthetic peptides too. So people would study natural peptides, figure out, all right, if I change these residues, what will happen? So a lot of this crossover between biology and chemistry happened starting in the late 60s, and it's still continuing today. I think that is where we are going to end it today. I've included the summary of reactions here. So the main ones are the Hell-Volhard-Zelinsky, the diethylmalonate variant for amino acids, the Strecker synthesis, the enantioselective synthesis, although I don't expect you guys to memorize the chiral catalysts, obviously. And then peptide bond formation, so knowing what protecting groups are needed for protecting and deprotecting. So Bach is the big one. Protecting groups for carboxylic acids were big. And really that's it. I'm not going to go into the nitty-gritty of directed evolution or anything like that. I'll leave that for your advanced classes. If you guys get a chance, though, this article that I posted on the website is super duper fascinating. So I put it down at the bottom here. It's the topic of the week. And these chemists were battling it out over the future of chemistry. So are the synthetic biologists going to win out, or are the organic chemists going to win out, or is it going to be a happy harmony between the two? It's a big debate, but these chemists are very, very famous. Phil Baran is like the rock star of chemistry right now. He's relatively young for a rock star chemist, but he's doing amazing work. And then the other two are cutting edge synthetic biologists. So the question is, will the future be dictated by synthetic biology or by organic chemistry? It's a really interesting read, and if you have a chance, I recommend it.